So in understanding polarity, it can be compared to a magnet. And we know on a magnet, we have a positive end and a negative end, or a positive pole and a negative pole. So in relation to polarity in chemistry, instead of a magnet, we have molecules. And these molecules are able to have both a positive pole and a negative pole. So that is polarity. It's essentially having two distinct positive and negative poles. But how do we determine if a molecule has polarity, whether or not it is polar or non-polar? So polarity can be determined by two characteristics. So electronegativity of an atom and the geometry of the overall molecule. So electronegativity it's the tendency of an atom within a molecule, and that atom will attract electrons to itself. So essentially, electronegativity is that how much does an atom like electrons? If an atom likes electrons more, it will have a higher electronegativity. So if we take a look at the electronegativity values, we can see that hydrogen has an electronegativity of 2.1. If we compare that to oxygen, which has an electronegativity of 3.5, we would say that oxygen has a higher electronegativity compared to hydrogen. And that is because oxygen has a greater tendency to attract electrons. Since it has that greater tendency, that it has that higher electronegativity. So the electronegative difference between two atoms can help determine whether or not a molecule is polar or non-polar. So if we have, for example, water, which is H2O. So in H2O, we've got hydrogen and we have oxygen. So if we take the electronegative difference, so if we take the difference, we would say 3.5 is oxygen, subtract hydrogen, which is 2.1, and we would get 1.4. This is our difference in electronegativity. So depending on each textbook, the parameters will be different, but essentially, if the electronegativity difference is greater than 0.4, the molecule is polar. If the electronegativity is less than 0.4, it will be non-polar. So if we're less than 0.4, it is non-polar. And if we are greater than 0.4, it is polar. So the first way to determine, the first characteristic to determine if a molecule is polar or non-polar is finding the electronegativity difference. If the electronegativity difference is greater than 0.4, it is polar. If it is less than 0.4, then it is non-polar. And in this case, the electronegativity difference between oxygen and hydrogen, it is 1.4. Therefore, we say water is polar. And that can be done for various elements. And fluorine is the molecule which has the highest electronegativity of 4.0. Now, the second characteristic that determines whether a molecule is polar or non-polar is geometry. And geometry is very important because if sometimes we may think that a molecule is polar because of the electronegativity difference, but it may not be because of the geometry. So let's take an example of carbon dioxide. Carbon dioxide has oxygen and carbon. So let's take the difference between the two. Let's find the electronegative difference. Carbon is 2.5, oxygen is 3.5. So if we take 3.5 of oxygen, subtract the 2.5 of carbon, we will get 1. Now, we could say that, okay, the electronegative difference is greater than 0.4, so carbon dioxide should be polar. but that is not true, and that is because of the geometry. The geometry of carbon dioxide is linear. So we see this structure for carbon dioxide. So this linear structure of carbon dioxide cancels out the two dipoles. So if we have the partial negative dipole here, we have that another partial negative dipole here. These two dipoles will cancel each other out, because if I draw out one dipole like this, because these dipoles are of the same magnitude, and I draw the second dipole, since they're of the same magnitude, equal and opposite in the same direction, they will cancel out. So that means that even though we may think that carbon dioxide is polar because of its electronegativity difference, it is actually non-polar because of its geometry. And this is a very important characteristic to determine if a molecule is polar or non-polar. So we see this idea of geometry in several other molecules, including nitrogen, which is a diatomic molecule. So nitrogen is always found in a pair, so it's always N2. So it also has that linear shape, so it's non-polar because the dipoles are equal and opposite, they cancel out. Same with oxygen gas, it's also non-polar. As we just mentioned, carbon dioxide is also non-polar. But ammonia is polar and hydrogen sulfide are polar. And that is because our dipoles are not in the same, are not equal and opposite. They are different in direction, so they are not canceling each other out. So we see a dipole moment here, and we see a dipole moment here. So we connect them head to tail, and we take, this would be our total dipole moment. So this is why this is polar. The dipoles are not canceling each other out. Same with over here, we see a dipole moment here, and another dipole moment here. None of these cancel each other out because they are not equal and opposite. So ammonia is also polar. So some common examples to help explain how geometry impacts polarity. One of the most easiest examples is of water. So water is H2O. We see the oxygen, central oxygen atom bound to two hydrogens, and it has two lone pairs. So once again, the dipoles are in opposite, are not canceling each other out. We'll see hydrogen have a partial positive charge, and oxygen will have a partial negative charge because it is attracting those electrons more because it has that higher electronegativity. The electron geometry of water is tetrahedral because we've got the two lone pairs and we've got the two hydrogen bonds, but the overall shape of water is bent. So the molecular geometry is bent. So since the dipoles are not in opposite directions, they do not cancel each other out. So water is polar. Water is also polar because the electronegativity of water is greater than 0.4. Carbon dioxide is nonpolar. It is nonpolar because of its geometry. So carbon dioxide, since it looks like this, it is nonpolar. Now, this third example, we have a central silicon atom bound to 4 chlorines. Now, this is also a tricky example, but if we keep in mind of equal and opposite dipoles, we can quickly understand that this is going to be non-polar because these 2 chlorines will cancel each other out, and these 2 chlorines will cancel each other out because equal and opposite magnitude dipoles. Now, the last one is a sulfur atom, central sulfur atom, bound to an oxygen, bound to an oxygen, bound to an oxygen, And we see that oxygen has its 3 lone pairs. But what's interesting about this one is that we may think that since the oxygens are creating dipoles equal and opposite of one another, they'll cancel out. But we have to keep in mind that of the electron geometry and the molecular geometry. The electron geometry is a tetrahedral, but the molecular geometry is trigonal pyramidal. So these two are not exactly equal and opposite of one another. The bond angle is actually 107 degrees approximately. So this is actually going to be a polar molecule because these oxygens are not equal and opposite. So there's a couple of tricky ones, but we just have to keep in mind of what molecular geometry we're looking at, what the bond angle is. If it's a perfect tetrahedral or if it's linear, then it's going to cancel out and be nonpolar. But if we see trigonal pyramidal or if we see this bent shape, it is going to be polar. Now, some common polar molecules in biochemistry include CO bonds, HO bonds. So a CO bond is a carboxyl or a carbonyl. So the difference between a carbonyl and a carboxyl is quite simple, but it can often be confused. So a carboxyl essentially is a carbon. In both carboxyls and carbonyls, we see that double bonded oxygen. But adjacent to this carbon, if we see another carbon, this is a carbonyl. But if we have a double bound oxygen and an OH group, this is a carboxyl. So the way I remember it is that if there's an OH groups are commonly classified as hydroxyl groups. So if the double bound oxygen has an OH, it is a carboxyl. If the double bound carbon-oxygen bond has a carbon, it is a carbonyl. So the OH distincts whether if it's a carboxyl or a carbonyl. Now, an OH is commonly, we see OHs in alcohols, we see HN bonds in they're amino bonds, and we'll see these in amino acids. So an HS bond, that's a thiol bond or a sulfur hydryl bond. A PO is a phosphate or a phosphoryl bond. And all of these bonds are very commonly found within biochemistry.